So as we begin lesson 13, it's important to point out that both lessons 13 and 14 are going to deal with waves directly. In lesson 13, we're going to introduce wave properties, and in lesson 14, we'll continue that and actually work with specific waves, dealing with concepts from how do you relate the wavelength to how many waves happen in a set period of time. All of that will come in lesson 14. And so for lesson 13, we're going to keep our discussion focused primarily on wave properties. What do we know about waves? How do waves actually work? How do they function? And as we get into exam 4, which we'll do next week, what you're going to need to know about waves is just going to be these properties that we're going to talk about. So first question that's important for us to deal with is this one. What are waves? How do they actually work? So first thing, waves are rhythmic disturbances that carry energy. What we mean by disturbances is that they impact the medium, whatever the medium is. If the medium is water, they impact that water. You recognize it by the movement of materials. Rhythmic gives you this idea of a very regular occurrence, and you'll see that characteristic of waves as we get into some more details. And then carry energy. This is probably the most important part of wave properties, because no matter the type of wave, you get a transfer of energy. Not all waves have the same obvious disturbance in the medium, but they all are carrying a disturbance of the energy inside of the medium. And then, regardless of the type of wave, waves are a rhythmic disturbance, but waves come in two broad categories. The first of which are mechanical waves. These are waves that actually require matter to transfer energy. A good example of these, or several examples of mechanical waves, sound waves. So the way sound moves from one area to another is a good example of a mechanical wave. Ripples, when you throw a rock into a body of water, and you can see the ripple away from that point of impact. Ocean waves, earthquakes, wave of people at a sporting event. All of these are mechanical waves. So they are, like all waves, disturbances that carry energy, but mechanical waves require matter to be present. Then you have electromagnetic waves. These do not require matter, so they don't require an actual medium to move. However, they do pass through a medium. So some examples of these: light. Light is probably the best example of electromagnetic waves. And so light does not need matter in order to move and transfer energy like waves do, but light can pass through mediums. Light can travel through water. Light can travel through air. Light can travel through other objects, but light does not require those objects in order to move and carry that energy. Then waves also come in two shapes. So waves come in two forms, also come in two shapes. The first is what are called transverse waves. And so in a transverse wave, if the energy is carried this way, the medium is displaced this way. So energy is carried this way, and the medium is displaced this way. These are probably the most common waves, the waves that you're most familiar with, and we'll talk about some of these. But ocean waves are a great example of this. So if here's your ocean wave moving this way, so energy is carried this way towards the shore, what you see as that wave is the displacement of water upward. That's a great example of a transverse wave. The other type of wave, or the other shape of wave, are called compressional or longitudinal. Most often referred to as longitudinal waves, but sometimes referred to as compressional. So if energy is moving this way in the wave, the material or the matter is also displaced this way. These are less common waves to interact with in terms of what you're actually thinking about. But sound travels this way, and I'll show you in a future slide a better example of this than just telling you sound, and show you how it actually works. So here's a transverse wave. So this is the direction of energy movement. And then here is the displacement. And again, a great example of a transverse wave is an ocean wave. And so there are a few terms that you have to think about when you're thinking about transverse waves. The crest is the top, the highest point of the wave, the highest point of displacement. Trough is the lowest point of displacement. Wavelength is the distance between from either crest to crest or trough to trough. So I'm going to redraw this wave over here, and then this would be a wavelength. And again, you either go from wavelength, you either go from trough to trough, or you go from crest to crest. That's a wavelength. And then amplitude is the distance between the midpoint and the highest or the lowest point. So this right here is the amplitude. And so the question you oftentimes get with amplitude, take this down here and write this question, is how much displacement? Remember, in a transverse wave, the matter that in the medium, the matter that the wave is traveling through, is displaced perpendicular to the carry of energy, to the movement of energy. So with amplitude, you're asking how much displacement has happened. Here's the midpoint of this wave. How much does that material get displaced away from that midpoint? So in an ocean wave, how far is the water going up, or how deep is the water going down below the normal level of that water? And down at the bottom here, we have our compressional or longitudinal wave, but we'll come back to that in a little bit. I want to continue to talk about transverse waves. Actually, let's deal with these compressional waves now, and then we'll go back to longitudinal waves. So in compressional waves or longitudinal waves, you have some different terms involved than what you had in transverse waves. So again, in a longitudinal wave, energy is moving in this direction, and that's the same direction that matter is displaced. So energy is moving in that direction, matter is being displaced in this direction. Okay? Matter is being displaced in this direction, energy is moving in that direction. First term we need to talk about is compression. Compression is where you end up with particles being crowded together. Here's a compression, here's a compression, and here's a compression. These are places where you have matter being crowded together relative to where it was before. Another term that you have to deal with is called rarefaction or rarefaction. This is the part in which the particles are actually being spread apart from where they were before. And so you can get some rarefaction here, and you actually looks like we have some additional examples of it here, and at least in this portion here, where you get the matter actually being spread out from where it used to be. And again, keep in mind, in a longitudinal wave, energy is moving in this direction, and displacement is happening in that direction. Okay. And then wavelength, you still have that term. Wavelength is the distance from one compression to another compression, and then or from one rarefaction to another rarefaction. And so this diagram actually has it illustrated improperly. That is two wavelengths. So one compression to another compression would be here. This is the wavelength. And then you can see that also modeled here. This is incorrect as well. You could go from here to here, one rarefaction to another rarefaction. This diagram has the wavelength illustrated longer than what it actually is. So it's the distance from one compression to another compression, either one area where particles are crowding to another area where particles are crowding, or from one rarefaction where particles are spreading out to another location where particles are spreading out. So I wanted to put this into this diagram because this provides us a great opportunity to actually talk about the electromagnetic spectrum. This electromagnetic waves, again, are waves that do not require matter to move. The electromagnetic spectrum is the spectrum of those waves that are possible. Notice here we're referring to these in wavelengths. And again, wavelength is the distance from crest to crest or trough to trough. So this right here would be wavelength. And so as you move to the right on this electromagnetic spectrum, our wavelengths are getting shorter. So as you move to the left, wavelengths are getting longer. And we'll talk next week or not next week, but in lesson 14 about what does that actually mean as far as the amount of energy that these waves contain. But this is a good opportunity to start talking about this. Okay, so this question here is a good one. Which of the following has the longest wavelength? Microwaves, gamma rays, radio waves, or ultraviolet light? So notice here we have some of these examples. Here are gamma rays. Here are microwaves. Here are radio waves. And what was the other one? Ultraviolet light. Here's ultraviolet light. Remember, as you move left on here, our wavelength is increasing. So radio waves have the longest wavelength. And then if you go down here, and again, we're not going to talk about frequency a great deal until we get into lesson 14, but frequency and wavelength are inversely related, which means if wavelength goes up, frequency goes down. And we'll talk about this in a lot more detail in lesson 14, but that's an important concept to remember. So which of the following has the highest frequency? It's going to be the one with the shortest wavelength, which was gamma rays. Gamma rays have the shortest wavelength. Remember that as you move to the right, wavelength decreases. So since gamma rays have the shortest wavelength, they're going to have the highest frequency. And so, now you'll note just a small portion of this is actually part of what's called the visible spectrum. You can see it written right here in this diagram. That's the visible portion of the electromagnetic spectrum, the part we can actually see. And that only comprises a very small amount of what is actually able to be seen. All right, so now we're going to work through a couple of problems, and then we'll be done with lesson 13. So first one, draw a transverse wave with a wavelength shorter than the amplitude. So here's the midpoint of our wave, and then with a wavelength that is shorter than the amplitude. So what we could do is just do a really big amplitude and a really small wavelength. And so here would be our wavelength, and then here would be our amplitude. We actually may need to exaggerate it a bit more. So let's redo this, and let's give a big amplitude and a very small wavelength. Okay, and so now here's our amplitude, and here's our wavelength. Remember, wavelength are crest to crest or trough to trough. And so this would be a transverse wave with a wavelength that is shorter than the amplitude. That is, the distance from crest to crest is less than the displacement of our materials. Draw a transverse wave with a wavelength twice as long as the amplitude. So let's get this midpoint again. Here's our amplitude. And so if we want something twice this long, we're going to want a wavelength that's about like this. It would be about twice as long. And so got to make sure we get back to our crest at that point. And so here's our amplitude, and then here's our amplitude. And up there, amplitude, there's our wavelength, and we have drawn a transverse wave with a wavelength twice as long as the amplitude. Keeping in mind that transverse waves, the displacement is perpendicular to the movement of energy. Energy is moving this way, and displacement is perpendicular to that. So that's the direction displacement is happening. All right, next one. Draw two transverse waves that have different wavelengths. So let's do this. Let's actually draw them on the same diagram. So here's one wave. Let's get a different color for our pen. Go with a blue pen. And there are two transverse waves. Let's get our red pen back so we can finish off this. And there are two transverse waves that have different wavelengths. Here's the wavelength for our red wave, and here is the wavelength for our blue wave. So we've got two transverse waves that have different wavelengths. The last one, draw two compressional waves with different wavelengths. Keeping in mind that compressional waves, the displacement and the energy go in the same direction. So energy is in this direction, as is displacement, or the movement of matter. So matter is moved in the same direction as the transfer of energy. And again, remember that sound waves are a good example of compressional or longitudinal waves. And also remember that waves, the wavelength in a longitudinal wave is the distance from one compression to another compression. So here are evidences of crowding, and then here it'll spread out, and here it'll go to crowded again, and here it'll spread out, and then here it'll go to crowded again. Okay, so here would be one wavelength, and then here let's switch colors so we can get our other compressional or longitudinal wave. Here's crowding, spreading out, evidence of crowding, spreading out, and crowding again. And so here would be the wavelength here. So here are two compressional waves with different wavelengths. And again, I just want you to keep in mind that when you're talking about properties of waves, wavelength is a very important concept. Now, it's different whether you're dealing with a transverse wave or a longitudinal wave, but wavelength is still a very important concept. When we talk about, frequency of sound, and higher pitches are, more difficult for people to hear than lower pitches sometimes, or there's, things that are too low for us to hear or too high for us to hear. All of that is in referencing to this wavelength. The longer the wavelength, the lower the frequency. So if you have a high frequency sound, something that would be very high pitched, you have a very small wavelength. And if you have a very low sound, you'd have something that has a very low frequency or a very long wavelength. Again, keeping in mind that frequency and wavelength are inversely related. As wavelength goes up, frequency goes down. Again, this is a concept that we'll pick up again when we're dealing with lesson 14, but it's an important concept to be introduced to now.